When we say that quantum behavior is fundamentally different from everyday physics, we are highlighting one of the most important and revolutionary discoveries in the history of science. For centuries, humans believed that the universe operated like a giant, predictable machine. Every cause had an effect. Every motion followed clear rules. Objects had solid positions, definite speeds, and easily measurable properties. This scientific world, based on common sense and classical physics, seemed universal and unbreakable. After all, we observe these rules every day. If you throw a ball, you can predict where it will land. If you push a book, it slides. If you turn on a light, electricity flows through wires in a steady, orderly way. Classical physics gave us the laws of motion, gravity, thermodynamics, and electromagnetism, and for a long time, people believed this was all the universe needed to run smoothly. However, everything changed in the early 20th century. When scientists began investigating atoms, electrons, and the tiniest particles in nature, they found that their familiar rules no longer worked. The universe was behaving differently at small scales, almost as if it had a second set of laws. Classical physics, which had successfully described planets, machines, bridges, and chemical reactions, suddenly failed to explain simple experiments involving light, electrons, and atoms. Nature did not behave like the predictable machine scientists had imagined. Instead, it acted strange, unexpected, and deeply confusing. This strange behavior became known as quantum physics, a completely different framework of rules that governs the microscopic world. And the relationship between classical physics and quantum physics is not like two versions of the same idea. They are fundamentally different in structure, logic, and consequences. What makes quantum physics quantum is not that it is complicated or advanced. It is that it contradicts almost everything we assume to be true based on our everyday experience. The surprising truth is that the world we see solid, stable, predictable, is actually built on a foundation of uncertainty, probability, and invisible patterns of energy. The difference begins with how quantum objects behave. In classical physics, an object is always in one specific place at a time. A car is either on the road or not. A bird is either on the branch or flying in the sky. A planet orbits along a clear path. But quantum objects do not follow this simple idea. When left unmeasured, a quantum particle can exist in several places or states simultaneously. It doesn't pick one until it is observed. This is known as superposition, one of the strangest and most important concepts in quantum theory. An electron inside an atom does not orbit the nucleus like a tiny planet. Instead, it exists as a cloud of possibilities. Its position is not a single point, but a spread out wave of probabilities. It is as if nature itself refuses to commit to one reality until a measurement forces a choice. This alone shows a profound difference. In the everyday world, things simply are where they are. In the quantum world, things can be many things at once. Another fundamental difference appears when we examine how particles move. Classical physics assumes motion is continuous. If something travels from point A to point B, it passes through the intermediate space smoothly. But in quantum physics, energy and movement occur in discrete packets, known as quanta. Light is not a continuous wave. It comes in packets called photons. Electrons in an atom do not smoothly slide between energy levels. They jump abruptly from one level to another without existing in between. These quantized behaviors do not appear anywhere in the everyday world. You cannot jump floors in a building without passing through the hallway, yet electrons do exactly that inside atoms all the time. The quantum world also introduces randomness in a way that classical physics never allowed. In everyday life, randomness is usually just ignorance, like not knowing the face of a card in a deck. But in principle, the card has a definite identity whether you see it or not. Classical randomness is only human unawareness. Quantum randomness is different. It is built into nature itself. A particle can behave in unpredictable ways not because we lack information, but because its behavior is truly probabilistic. The same experiment performed the same way can give different outcomes, and there is no deeper hidden rule determining which outcome will occur. Nature, at its core, contains uncertainty. This idea shocked great scientists like Einstein, who famously said, "God does not play dice." But repeated experiments showed that quantum randomness is real and fundamental. Quantum uncertainty is not a flaw, it is a natural limit. This is not how planets behave. Planets do not randomly choose where to move. They follow predictable orbits. But quantum particles take paths that can only be described by probabilities. This is another deep divide between the quantum and classical worlds. One of the most dramatic differences comes from the role of measurement. In classical physics, measuring something does not change what it is. A thermometer tells you the temperature, but it doesn't change the temperature. A ruler measures length without making the object shrink or grow. But in quantum physics, observation affects the system. The very act of measuring can collapse superpositions, freeze possibilities into definite outcomes, and influence how a particle behaves. This is known as the measurement problem, a unique and unnatural idea compared to classical physics. It suggests that the observer and the observed are not separate entities. In the quantum world, observation is not passive. It participates in creating the result. These differences are not small. They redefine what reality even means. In classical physics, reality exists independently of us. In quantum physics, reality becomes defined at the moment it is measured. This is something so unusual that even today physicists debate its interpretation. Another major difference is entanglement, a phenomenon in which two particles become linked so deeply that the state of one instantly affects the other, no matter how far apart they are. If you separate two entangled particles by thousands of kilometers, changing one will change the other immediately. This type of connection has no classical equivalent. There is nothing in everyday experience that behaves this way. Entanglement violates classical ideas about locality, which is the idea that objects can only influence each other through direct contact or signals traveling through space. Quantum entanglement suggests that at the deepest level, the universe may be more connected than we imagine. While classical physics treats objects as separate and independent, quantum physics reveals that some particles behave as if they share a single unified state. This concept is not only strange but deeply important, forming the basis for quantum computing and quantum communication. A core reason that quantum behavior feels foreign to us is that we never directly observe quantum effects in our daily lives. This is because quantum behavior becomes significant only at extremely small scales, far smaller than the width of a human hair. When many quantum particles come together, their quantum effects tend to average out, creating the smooth, predictable behavior of the classical world. In other words, classical physics is not wrong. It is simply a large-scale approximation of quantum physics. The classical world is the surface. The quantum world is the foundation. If we were small enough to see electrons the way we see apples, we would never expect classical behavior. The world would look fluid, uncertain, and probabilistic. There would be no solid boundaries, no definite positions, and no clear cause and effect patterns. What feels weird to us is perfectly natural at the quantum scale. The weirdness is a consequence of our limited human experience. Quantum behavior also challenges traditional logic. In everyday life, something cannot be two contradictory things at once. A switch is on or off, a person is here or there, but quantum objects can exist in mixed states that sound impossible by classical logic. This is not because they defy logic, but because classical binary thinking is insufficient for describing the complexity of quantum reality. Some researchers argue that quantum mechanics requires a new kind of logic, a logic based on probabilities, uncertainty, and overlapping possibilities. Another aspect of quantum physics that differs from classical physics is wave-particle duality. In classical physics, waves and particles are fundamentally different. Waves spread out, interfere, and overlap. Particles are localized and discrete, but in quantum physics, particles exhibit wave-like behavior, and waves can behave like particles. Light can be both a wave and a particle. Electrons can create interference patterns like waves. At a deep level, quantum entities cannot be classified as strictly particles or waves. They are something more fundamental, which can display either behavior depending on the context. This dual nature defies classical categories. It forces scientists to rethink the basic building blocks of nature. Instead of being solid, tiny marbles, particles are better thought of as mathematical probabilities that manifest differently under different conditions. The mathematical framework of quantum physics itself highlights the difference. Classical physics uses numbers that represent exact values. Quantum physics uses wave functions, which encode probabilities, amplitudes, and complex, valued expressions that describe the full range of possible states. These wave functions do not exist in physical space the way objects do. They exist in an abstract mathematical space, yet they guide the behavior of real physical particles. This introduces a divide between mathematical description and physical reality that classical physics never had. Quantum physics also introduces limits that do not exist in classical physics. The Heisenberg uncertainty principle states that certain properties, like position and momentum, cannot both be known with perfect accuracy. The more precisely one is known, the less precisely the other can be known. This is not a limitation of measuring instruments. It is a fundamental property of nature. In classical physics, you can always imagine measuring both position and momentum perfectly, even if you lack the tools. In the quantum world, the limit is built into reality. Finally, the scale on which quantum behavior dominates is extremely small, but the implications are enormous. Quantum physics explains the structure of atoms, the formation of chemical bonds, the nature of light, and the stability of matter itself. Without quantum rules, electrons would spiral into atomic nuclei, and atoms would collapse. The everyday world exists only because the quantum world behaves so differently. Classical physics describes the world we see. Quantum physics explains why the world can exist at all. Quantum behavior is fundamentally different from everyday physics because the quantum world operates on principles that defy our natural intuition. It is a world governed by probabilities rather than certainties, by states rather than locations, by waves and particles that merge into one, by entangled pairs that remain connected beyond distance, by energies that jump in discrete amounts, and by outcomes that only become real when observed. Classical physics is smooth, continuous, predictable, and intuitive. quantum physics is discrete, probabilistic, interconnected, and counterintuitive. These differences are not minor, they reshape our understanding of what reality truly is. The universe is not built from tiny classical balls following straight paths. It is built from quantum entities following rules that are elegant, mathematical, and astonishingly strange. To further understand why quantum behavior is fundamentally different from everyday physics, it is helpful to look more closely at the experiments that revealed these strange patterns. In the early days of physics, scientists expected that studying smaller and smaller phenomena would simply refine the rules of classical mechanics. Instead, every experiment at microscopic scales produced results that classical physics could not predict. These experiments were not obscure or rare. They were simple demonstrations showing that nature behaved in ways that seemed completely impossible. One of the most famous examples is the double-slit experiment, which revealed the wave-like behavior of particles such as electrons. Imagine firing tiny particles, one at a time, through two narrow slits onto a screen. Classically, each particle should pass through one slit or the other and form two distinct clusters. But electrons instead create an interference pattern, a pattern of alternating bright and dark regions, something typically observed with waves like water or light. Even stranger, this wave-like pattern appears even when electrons are released one at a time, meaning each individual particle somehow interferes with itself. This is a clear sign that the particle exists in multiple states or paths at once, a direct violation of classical expectations. However, when scientists place detectors at the slits to check which path the electron actually takes, the interference pattern disappears. The particles suddenly behave like classical particles, creating two clusters instead of a wave-like pattern. Simply observing the electron collapses its multiple possibilities into a single outcome. This is not a small adjustment to classical theory. It completely overturns our understanding of what it means for something to have a path, a location, or a definite behavior. The double-slit experiment alone reveals almost all the core differences between quantum and everyday physics in a single demonstration. Another important experiment is the photoelectric effect, which helped launch quantum theory. Classical physics predicts that shining a bright enough light on metal should eventually knock electrons out of it, because increasing brightness should increase the energy carried by light. But this is not what happens. Even extremely bright light will fail if its color or frequency is too low. On the other hand, even a very dim light of the right frequency can immediately release electrons. This only makes sense if light comes in discrete packets, photons whose energy depends on frequency, not intensity. This discovery shattered the classical view of light as a purely continuous wave. It forced scientists to accept that energy itself is quantized. These experiments illustrate why quantum physics is not just a modification of classical physics, but an entirely new way of viewing reality. Classical physics relies on determinism, meaning every event follows precisely from earlier causes. If you know all the forces acting on an object, you can predict its future exactly. But quantum physics destroys this certainty. Even when all conditions are known perfectly, quantum experiments can yield different results each time. Only probabilities can be predicted, not definite outcomes. This randomness is not a sign of ignorance. It is a fundamental feature of reality. Nature chooses an outcome based on probability, not certainty. This idea is profoundly unsettling to anyone who believes the universe should follow strict laws. Yet quantum mechanics has been tested in countless experiments, and it always makes correct predictions. The quantum world is inherently unpredictable. One way to understand the difference is to imagine a coin flip. In everyday life, the uncertainty of a coin flip comes from not knowing the exact forces involved. But in principle, if you knew all the details, the speed, the angle, the air resistance, you could predict the outcome. Quantum uncertainty is different. Even if you know everything about the system, the outcome remains truly unpredictable until it is measured. It is as though the coin is not even in a definite state until it lands. This is one of the clearest divides between the classical and quantum worlds. Another major difference arises in how quantum particles can be correlated with each other. In classical physics, information cannot travel faster than light, and objects can influence each other only through local interactions. But quantum entanglement ignores these classical limits. When two particles become entangled, they share a single quantum state. Changing one instantly affects the other, no matter how far apart they are. This instantaneous connection puzzled scientists for decades. Einstein believed that quantum theory must be incomplete, because he thought nothing could transmit information faster than light. But experiments repeatedly confirmed entanglement, proving that quantum mechanics was correct and that classical limits did not apply in the microscopic world. Yet entanglement does not allow sending messages faster than light, so it does not break relativity. Instead, it reveals that the quantum world does not operate according to classical ideas of separation and independence. Entangled particles behave like a single unit, even when physically separated. This is not comparable to anything in everyday experience. You cannot separate two coins and flip one, expecting the other to instantly match. But quantum entanglement works exactly this way. It reveals a deep, invisible unity in the fabric of the universe, one that classical physics could never anticipate. The difference between quantum and classical physics also appears in how systems evolve over time. In classical physics, knowing the current state of a system allows you to predict its future. But in quantum physics, the wave function evolves smoothly until a measurement occurs, at which point it collapses unpredictably. This blend of deterministic evolution and random collapse has no classical counterpart. Scientists have debated for decades how to interpret the collapse of the wave function. Some believe collapse is a real physical event. Others think it is only a change in knowledge, not in the system itself. Still, others propose that all possible outcomes actually occur, but in different branches of reality. These debates exist because quantum behavior has no intuitive classical analogy. The classical world is predictable. The quantum world contains both predictability and irreducible randomness. Another contrast arises from the concept of locality. In classical physics, objects occupy definite places in space and influence each other only through direct contact or signals. In quantum physics, the wave function spreads across space, meaning the state of a particle is not localized until measurement. This means a particle can be in multiple regions simultaneously, a phenomenon with no classical counterpart. When a measurement occurs, the wave function collapses instantaneously across space. This non-local collapse cannot be explained by classical signals traveling at finite speeds. It indicates that quantum reality is not constrained by classical ideas of space and distance. Classical physics treats space as a container in which events unfold. Quantum physics suggests that space may be a secondary feature, emerging from more fundamental connections. Even the stability of matter depends on quantum rules. In classical physics, electrons orbiting a nucleus would lose energy continuously and spiral inward, causing atoms to collapse. But quantum physics introduces stable energy levels, preventing electrons from losing energy except in quantized jumps. This stability allows atoms to exist, molecules to form, and matter to have structure. Classical physics cannot explain why matter doesn't collapse. Quantum physics explains why matter is stable. This again reveals that classical rules are incomplete. A common misunderstanding is that quantum behavior is simply weird. But quantum physics is not weird to nature. It is only weird to us because our senses evolved to operate at scales where quantum effects average out. The classical world we see is not the true foundation of reality. It is the large-scale result of quantum systems acting together. When billions of atoms interact, their individual quantum behaviors blend into smooth, predictable patterns. This creates the illusion that the world is classical. But underneath every solid object, every chemical reaction, every beam of light, quantum rules govern everything. The transition from quantum to classical behavior is still an active area of research. Scientists want to understand how definite outcomes emerge from uncertain quantum states. One explanation is decoherence, the idea that quantum systems lose their coherence when they interact with the environment. When a system is isolated, it can remain in superposition, but when it interacts with the environment, air molecules, light, heat, these interactions effectively measure the system, collapsing the superposition. Decoherence explains why quantum effects are rarely visible at large scales. Our everyday world is filled with constant interactions, making superpositions impossible to sustain. But in controlled laboratory conditions, quantum effects can be preserved, enabling technologies like quantum computing. Quantum computing itself highlights how radically different quantum behavior is from everyday physics. Classical computers process information using bits that represent 0 or 1. Quantum computers use qubits that can exist as 0, 1, or both simultaneously due to superposition. Entanglement allows qubits to share states, meaning the state of one qubit depends on the state of another, even across distances. These features allow quantum computers to perform certain calculations far faster than classical computers. No classical system can replicate these quantum effects. The existence of quantum technologies is a direct demonstration that quantum rules are profoundly different from classical ones. Quantum tunneling provides yet another clear example of this difference. In classical physics, an object cannot pass through a barrier unless it has enough energy to overcome it. But in quantum physics, particles can tunnel through barriers even when they lack the necessary energy. This is because quantum particles are described by wave functions that extend beyond classical boundaries. Tunneling is essential to processes like nuclear fusion in stars, radioactive decay, and even modern electronics. Without quantum tunneling, the sun would not shine and life would not exist. Classical physics cannot explain this phenomenon. It only makes sense in the quantum framework. Quantum fields add another layer of distinction. In classical physics, fields like the electromagnetic field fill space and influence objects. In quantum physics, fields are quantized, meaning particles are simply excitations or disturbances in these fields. The quantum field theory framework shows that particles are not independent entities. They are fluctuations in underlying fields. This perspective has no equivalent in classical physics, where particles and fields are distinct. The idea that matter and energy emerge from quantized fields is one of the greatest shifts in scientific thinking. It transforms the meaning of particles, space, and interactions. Particles also behave differently when we consider their identity. In classical physics, objects are distinguishable. You can label two identical balls, A and B, and track their separate movements. But in quantum physics, identical particles are fundamentally indistinguishable. Two electrons cannot be labeled or tracked as individuals. Their states must be described jointly, and exchanging them produces no physical difference. This indistinguishability is essential to phenomena like the Pauli exclusion, principle, and Bose-Einstein condensation. These quantum effects explain why matter has volume, why atoms form ordered structures, and why materials behave differently at extremely low temperatures. Classical physics cannot explain why electrons avoid each other in atoms, or why certain particles can accumulate in identical states. These behaviors arise directly from the quantum identity of particles. The more we explore quantum physics, the more we realize how deeply it differs from classical physics in logic, behavior, and interpretation. Classical physics describes a world that is objective, deterministic, local, and continuous. Quantum physics reveals a world that is probabilistic, interconnected, quantized, and fundamentally uncertain. The same universe operates under both sets of rules, but the classical world emerges only as an approximation of the quantum world. Classical physics is like the surface of a deep ocean. It behaves predictably and smoothly, but beneath the surface lies a dynamic, fluctuating, probabilistic realm that determines everything above. Quantum behavior is fundamentally different because it forces us to rethink almost every assumption about reality. It changes our understanding of space, time, matter, energy, and information. It shows that certainty is not the foundation of nature. Probability is. It shows that objects are not isolated. They can be deeply entangled. It shows that signals do not simply travel through space. Connections can be instantaneous. It shows that matter is not made of solid particles. It is made of wave functions and quantized excitations. It shows that measurement is not passive. It actively shapes the outcome. And it shows that the classical world we trust and rely on is only a simplified reflection of a much richer, more complex quantum reality. The universe at its core is quantum mechanical. Classical physics works only because quantum effects average out at large scales. The fact that our world feels predictable is not a sign that quantum rules are rare, but that they are hidden from our senses. The classical world is the shadow, the quantum world is the source. Understanding these differences helps us appreciate the depth and beauty of the natural world. It reminds us that reality is not limited to what we see. It is shaped by principles that defy intuition yet allow everything, from atoms to galaxies, to exist. Quantum physics reveals a universe more unexpected, more mysterious, and more profound than any classical picture ever imagined. When we say that particles can exist in multiple states at the same time, we are describing one of the most astonishing and foundational ideas in quantum physics: superposition. This single concept turns our entire understanding of reality upside down, because everything in our daily lives behaves in exactly the opposite way. In the classical world, objects exist in definite states. A coin is either heads or tails. A light switch is either on or off. A car is either moving or parked. Even when we do not see something, we believe it exists in one clear state. If someone hides a ball behind a curtain, the ball does not disappear into a cloud of possibilities. It remains where it is, waiting for us to look. This idea, definite states existing independently of observation, is a natural part of human intuition and classical physics. But as soon as we enter the quantum world, this intuition collapses. Particles do not behave like tiny versions of familiar objects. Instead, they behave like mathematical waves of probability that spread out, overlap, and combine. A single particle, such as an electron or photon, does not have to choose one state. It can exist in a mixture of states simultaneously. Superposition is not simply a lack of knowledge about the state of the particle. It is not like saying, "We don't know where the particle is, but it is somewhere." Instead, superposition means the particle is genuinely in multiple possible states at once, not committing to any single one until a measurement forces a decision. This idea is extremely difficult to grasp because it has no parallel in ordinary experience. Consider a vibrating guitar string. The string can vibrate with multiple harmonics simultaneously, the fundamental frequency and several overtones. The string is not choosing one vibration. It carries all those frequencies at the same time. In a similar way, a quantum particle can carry multiple possibilities at once, multiple positions, multiple energies, even multiple paths. But the analogy only goes so far. The guitar string is still a classical object with definite physical properties. A quantum particle in superposition does not have definite properties until observed. The entire set of possibilities is real, not just a mathematical trick. To see why superposition matters, we can look at the double-slit experiment again, one of the clearest demonstrations of this behavior. When a particle such as an electron is fired toward two slits, it behaves as if it passes through both slits at the same time. It does not choose slit A or slit B. Instead, it exists in a superposition of both paths, interfering with itself like a wave. The interference pattern on the screen shows that the electron treated the two paths as simultaneous realities. This is not a case of the electron splitting in half. It is a case of the electron occupying multiple possible routes in a single superposed state. Only when a measurement device tries to detect which slit the electron went through does the superposition collapse into one clear path, and the interference pattern disappears. Superposition applies not only to position, but also to other properties such as energy, momentum, spin, and polarization. An electron's spin can be up and down at the same time until measured. A photon's polarization can be both horizontal and vertical simultaneously. A particle's energy can exist in a mixture of different levels. Even entire atoms can exist in superposed states under the right conditions. The laws of quantum physics allow this freedom because the mathematical equations describing quantum systems, particularly the wave function, are linear and allow combinations of possible states to form new valid states. It is important to understand that superposition is not metaphorical. It is not a convenient way of talking about probabilities. It is a real physical phenomenon. The wave function that represents the superposed state can be measured and manipulated directly. Interference patterns emerge only when superposition is preserved. When superposition is destroyed, interference disappears. This difference allows scientists to verify that superposition is not an illusion. It is a fundamental property of nature. The idea of superposition is so counterintuitive that even great physicists like Schrödinger used thought experiments to illustrate just how strange it is. His famous example involves a cat inside a box with a quantum, triggered device. If the trigger is based on the superposition of a radioactive atom, then the cat becomes entangled with the atom's superposed states, alive and dead at the same time. Schrödinger did not propose this idea to suggest that cats literally exist in such a state in everyday life. He proposed it to show that superposition, when extended to everyday scales, defies logic and exposes the sharp divide between quantum and classical reality. The thought experiment challenges us to ask where and how superposition collapses into definite states. The cat paradox reveals that superposition is not a conceptual trick. It is a principle with very real, very strange implications. Another important aspect of superposition is that it has no classical limit. In classical physics, combining states is meaningless. You cannot combine moving left and moving right into a single state. You cannot combine on and off. But in quantum physics, linear combinations of states are fundamental. A quantum system can exist in a state that is 50% upspin and 50% downspin. When measured, you never see a half up, half down result. You see either up or down. But before measurement, the system genuinely exists in both states simultaneously in a complex mixture. The wave function describing this mixture captures the probabilities of each outcome and governs how the system evolves over time. The collapse of superposition upon measurement is one of the greatest mysteries in physics. Why does a quantum particle behave as a spread out wave of possibilities before measurement, but behave like a definite particle after measurement? What counts as a measurement? How does nature decide which outcome becomes real? Different interpretations of quantum mechanics attempt to answer these questions. Some argue that the wave function collapse is an actual physical process. Others argue that all possible outcomes occur in separate universes. Still, others claim the wave function never collapses, observers simply become entangled with the outcomes. But despite these disputes, all interpretations agree on the fundamental fact: superposition exists and determines the behavior of quantum systems. Superposition also helps explain many physical phenomena that classical physics cannot describe. Electrons in atoms do not orbit like planets. Instead, they occupy superpositions of different energy levels and spatial configurations. These superposed states create the shell structure of atoms, determining how they form chemical bonds. Chemical reactions depend on superpositions of electron states. The colors of objects, the conductivity of materials, and the stability of matter all rely on superposition. Without superposition, atoms would behave like tiny solar systems and collapse, and molecules would not form in the stable, structured way they do. Another dramatic demonstration of superposition appears in quantum computing. A classical bit stores either 0 or 1. A quantum bit, or qubit, can store both 0 and 1 simultaneously in superposition. This means that a collection of qubits can represent enormous amounts of information at once. For example, while classical computers must check each possible solution to a problem one at a time, quantum computers can process superpositions of many solutions simultaneously. This parallelism allows quantum computers to potentially outperform classical computers in tasks like cryptography, optimization, and molecular simulation. The power of quantum computing comes directly from superposition, not from smaller or faster transistors. It comes from allowing physical systems to occupy multiple computational states at the same time. Superposition extends beyond isolated particles. Entire groups of particles can exist in collective superposed states. Superconductors and superfluids are examples of macroscopic quantum phenomena where superposition plays a central role. In these systems, large numbers of particles act as a single quantum entity, allowing currents to flow without resistance or fluids to flow without viscosity. Such behaviors seem impossible in classical physics because they require many particles to share the same superposed state. But quantum physics allows this kind of collective behavior by nature. The persistence of superposition is extremely fragile. The moment a superposed system interacts with the environment, air molecules, photons, vibrations, the superposition can collapse. This process, known as decoherence, destroys the delicate quantum combinations and forces the system into definite classical states. Decoherence explains why superposition is not visible in everyday life. Objects around us, tables, chairs, people interact constantly with the environment, making superposition impossible to observe on large scales. But when scientists isolate systems in controlled environments, superposition becomes visible and measurable. This suggests that the classical world emerges from the quantum world through the fragile nature of superposition. Superposition forces us to rethink the nature of reality itself. In classical thinking, reality is composed of definite objects with definite properties. Superposition suggests that reality, at its deepest level, consists of overlapping possibilities, not definite outcomes. A particle does not have a single location until it is measured. It does not have a single energy until it interacts with something. It does not have a single spin until an experiment forces it to choose. Before measurement, the particle's properties are not merely unknown. They do not exist in a definite way. They exist as probabilities encoded in the wave function. This is not just a theoretical idea. It is confirmed experimentally again and again. Superposition also raises philosophical questions about consciousness, observation, and the relationship between the observer and the observed. Does measurement require a conscious observer, or can any atomic-level interaction count as observation? While most physicists believe that consciousness is not required, the debate highlights the deep conceptual implications of superposition. It forces us to ask whether the world exists in a definite state before we look at it. The evidence increasingly suggests that it does not. Reality is not made of fixed states waiting to be discovered. It is made of probabilities waiting to be resolved. Superposition challenges logic, intuition, physics, and philosophy all at once. It reveals a universe where multiple realities coexist, merge, and interfere. The classical world we experience, with its solid objects and predictable behaviors, is only the visible outcome of countless superpositions collapsing into definite states through interaction. The quantum world is not hidden because it is rare. It is hidden because it is delicate. Deep down, the entire universe operates in superposed states, and the definite world we see emerges as a special case. To continue our deep dive into the concept of superposition, we need to extend our understanding from the quantum textbook definitions and step into the broader meaning of what multiple states at once actually implies. Part A focused on the foundation, how superposition works, what it means for particles to exist in overlapping possibilities, and why the idea challenges our classical understanding of reality. Motivation, but the second half of the discussion must push further, but only exists few learn to speak discipline fluently, but how it behaves, how we measure it, how it influences technology, and what philosophical implications it carries about the nature of our universe. Superposition is not just a clever scientific phrase. It is a window into a deeper version of existence. To visualize superposition in a deeper sense, imagine a coin spinning in the air. While spinning, the coin is not really heads or tails. it is in a dynamic, undefined state. But once the coin lands, it becomes one outcome or the other. This coin analogy is limited, but it helps show a subtle point. While the coin spins, uncertainty is simply because we don't know its orientation. The coin itself is still in one definite position at each moment. In quantum superposition, however, a particle is genuinely in all its possible states simultaneously, not because we lack knowledge, but because the particle does not commit to one version of itself until an interaction forces it to. This is not uncertainty by ignorance, it is uncertainty by nature. Understanding this difference is important because it reveals a unique truth. Quantum superposition is not representing hidden data, but an entirely new category of physical existence. The particle is not secretly one thing or another. It truly exists across possibilities in a blended, multi-state form. This is why quantum mechanics remains one of the most revolutionary discoveries in the history of science. It tells us that the universe does not evolve through fixed, predetermined states, but through layers of intertwined potentiality. Now, the next question becomes, what happens when we observe or measure a particle in superposition? Why does measurement seem to collapse its possible states into one definite outcome? To understand this, we must discuss the idea of decoherence, one of the most important and least understood concepts that bridges the quantum world with the classical world we experience. Decoherence happens when a particle in superposition interacts with its environment. Light, air molecules, electromagnetic fields, or even stray particles in space. These interactions disrupt the delicate superposition and force the particle to transition from a multi-state existence into a single, clear outcome. In essence, superposition is incredibly fragile, and the universe constantly tries to collapse it unless it is perfectly isolated. This fragility raises a question. If everything at the smallest scale is in superposition, why don't we see this in our everyday world? Why aren't tables, cars, or people blending between multiple states? The answer lies in scale. Macroscopic objects like humans, tables, or even dust particles are made of trillions and trillions of atoms. The interactions between all these atoms and their environment cause decoherence to occur instantly, long before superposition can have any noticeable effect. In contrast, single particles or small quantum systems can maintain superposition long enough for us to study and manipulate them. But there is something even more fascinating. Scientists can harness superposition deliberately. Through careful engineering, they can protect particles from environmental interactions using techniques like vacuum chambers, electromagnetic traps, and cooling systems that reach temperatures near absolute zero. By controlling these particles, researchers can observe effects that would otherwise be impossible, such as particles interfering with themselves. This interference is one of the strongest pieces of evidence that superposition is real. In the famous double-slit experiment, for example, a single particle behaves as though it passes through multiple paths at the same time. It does not choose until it is forced to choose. The pattern it creates, an interference pattern, proves that the particle experienced itself in multiple overlapping positions. To explore this idea even further, consider what happens if we place detectors at the slits to observe which path the particle takes. The moment we watch, the interference pattern disappears, and the particle behaves as though it passed through only one slit. This is one of the most profound results in modern science. Observation changes the reality of quantum systems. The act of measuring destroys the superposition, and the particle collapses into one outcome. This collapse is not caused by conscious observation. Any interaction with the environment qualifies, but it demonstrates the influence that information plays in shaping physical reality. Superposition also raises a fascinating philosophical question. Does a particle have a definite property before we measure it? Or does the act of measurement bring that property into existence? Many interpretations of quantum mechanics attempt to answer this. The Copenhagen interpretation says that properties don't exist until they are measured. The many worlds interpretation says that all outcomes happen, splitting into different branches of reality. The pilot wave interpretation suggests that particles have definite positions, but their wave functions guide them through a landscape of probability. The fact that multiple interpretations exist highlights one thing. Even after a century, humanity still struggles to grasp the full meaning of superposition. Now, superposition is not just a philosophical curiosity. It has practical, world-changing applications. It is one of the foundational principles behind quantum computing. Traditional computers store information in bits, which can be either 0 or 1. Quantum computers use qubits, which can exist in superpositions of 0 and 1 simultaneously. This means a quantum computer can process many possible solutions at the same time, giving it potentially unprecedented computational power. The very weirdness of superposition is what makes quantum computing so extraordinary. Every additional qubit doubles the number of simultaneous states the computer can represent. A classical computer would need more transistors than there are atoms in the universe to match what only a few hundred qubits could theoretically compute. Another technological application is quantum cryptography. Superposition allows secure communication because measuring a quantum particle changes its state. If someone tries to eavesdrop on a quantum encrypted message, the act of reading the information alters it, revealing the intrusion. This makes quantum communication one of the most secure forms of information transfer ever conceived. Superposition also plays a role in quantum sensing and metrology. Extremely sensitive devices use superpositions to measure tiny changes in gravity, magnetic fields, or other physical properties, far beyond what classical instruments can achieve. These devices can detect extremely small variations because superposition amplifies certain interference patterns or enhances precision through entanglement-based methods. Superposition even helps us understand how biological systems function. There is emerging evidence that quantum effects play a role in processes like photosynthesis, where energy seems to move through plant cells in superposition, like pathways simultaneously, finding the most efficient route. Some researchers speculate that birds use quantum superposition in their navigation systems, sensing Earth's magnetic field through quantum mechanisms in their retinas. If this is true, it means that nature itself has been exploiting quantum superposition long before humans understood it. This leads us deeper into the philosophical implications of superposition. If the fundamental building blocks of reality do not commit to a single state until forced, then the universe may be fundamentally probabilistic rather than deterministic. This challenges long-held beliefs that the universe operates like a giant, predictable machine. Instead, reality seems to unfold through dynamic patterns of possibility. The world we see is only one version among countless potential outcomes that could have occurred. Every moment of existence, down to the smallest scale, is shaped by probabilities interacting in complex ways. Superposition also raises profound questions about what measurement means. Does measurement require a conscious observer, or is physical interaction enough? Most scientists agree that consciousness is not required, but the debate touches on deeper questions about the role of information in the universe. If measurement is simply the acquisition of information, then reality may be inseparable from the information that describes it. Some physicists have even proposed that the universe is, at its core, an informational structure, and superposition is a key feature of how information behaves at the quantum level. Another interesting consequence of superposition is the boundary between the quantum and classical worlds. When does the transition occur? At what point does a multi-state quantum system become a single-state classical system? Understanding this transition is one of the major unsolved problems in physics. If scientists can fully understand decoherence and the collapse of superposition, we may unlock even deeper insights into the origins of the universe, the nature of time, and perhaps even the emergence of consciousness. In cosmology, superposition plays a role in theories like quantum gravity and the early universe. During the first fraction of a second after the Big Bang, the universe existed in a superposition of different energy states. Tiny fluctuations, influenced by quantum superposition, eventually grew into galaxies, stars, and planets. The structure of the cosmos may have emerged directly from quantum uncertainty. In this sense, superposition is not just a microscopic phenomenon. It helped shape the entire universe. To make the concept even more accessible, imagine a musical chord. When you play multiple notes at once, the sound is rich, layered, and filled with possibilities. Each note contributes to the harmony, and all coexist simultaneously. Only when you press one note alone does the sound collapse into a single tone. Superposition is like the universe's ability to play chords instead of single notes. It makes nature richer, more complex, and more beautiful than a purely classical world would allow. Ultimately, the second keynote particles existing in multiple states at once is not just a scientific fact, but a revolutionary concept that reshapes our understanding of what reality is. It challenges our intuition because we live in a world dominated by classical experiences. But superposition is not exotic. It is fundamental. Everything you see, touch, and experience is built on particles that behave in ways far stranger than anything in our normal lives. The everyday world emerges from the quantum world, not the other way around. If superposition were to vanish tomorrow, chemistry would collapse, atoms would be unstable, and the universe, as we know it, would fall apart. The stability of matter depends on quantum states overlapping and forming the structure of atoms. The vibrant colors we see are due to electrons transitioning between superposed states. The strength of materials, the behavior of light, and the functioning of life itself rely on quantum effects. So when we talk about superposition, we are discussing a principle that shapes everything from the smallest particles to the grandest cosmic structures. It is not a trick or an illusion. It is the blueprint of existence. The particle that exists in multiple states at once is more than a scientific mystery. It is a reminder that the universe is deeper and more complex than our senses reveal. Superposition teaches us to question our assumptions, to embrace uncertainty, and to understand that the true nature of reality is far more dynamic than our limited human experience suggests. Superposition is not just a fact of quantum physics. It is a window into the poetic, mysterious, astonishing architecture of the universe. It invites us to rethink everything we know and to appreciate the hidden layers of possibility woven into the fabric of existence. One of the most mind-bending aspects of quantum physics is that observation itself can change the outcome of an experiment. This phenomenon seems almost impossible from the perspective of everyday experience. In classical physics, observing an object does not alter its fundamental properties. If you measure the speed of a car, the car is not affected by the measurement. If you look at a book, it remains the same book. Observation is passive. It does not interfere with the underlying reality. Quantum physics, however, turns this idea completely on its head. At the quantum scale, the act of observing a particle, whether an electron, photon, or atom, can determine how it behaves. This concept is central to the quantum world and challenges our deepest intuitions about reality. The principle arises from the dual nature of quantum systems. Quantum entities, unlike classical objects, exist as probabilities described by a wave function. This wave function encodes all possible states the particle could occupy, along with the likelihood of each state. Before measurement, the particle does not reside in any single state, but rather exists in a superposition, a blend of multiple possibilities. The particle is not undecided because we lack information. It genuinely occupies all possible states simultaneously. When we observe the system, we force it to choose a particular state, a process often referred to as wave function collapse. The outcome of that choice depends probabilistically on the system's wave function, but the act of observation is what finalizes the result. Without observation, the system remains in superposition, exhibiting behaviors that would be impossible to predict classically. The classic example illustrating this effect is the double-slit experiment. When electrons or photons are fired toward a barrier with two slits, they produce an interference pattern on a screen behind the slits. This pattern is characteristic of waves and indicates that each particle is simultaneously exploring both slits and interfering with itself. Remarkably, this happens even if particles are fired one at a time. The particle seems to behave like a wave, traveling through multiple paths simultaneously. However, when scientists place detectors at the slits to observe which path the particle takes, the interference pattern disappears. Instead, the particles behave as if they traveled through only one slit, forming two simple clusters on the screen. The mere act of measuring which slit the particle passes through fundamentally changes the outcome. Observation transforms the behavior from wave-like to particle-like. It is crucial to emphasize that observation in quantum physics does not necessarily imply human consciousness. Any interaction capable of extracting information from the system counts as a measurement. A photon bouncing off an electron or a detector recording the particle's presence qualifies as observation. These interactions cause decoherence, destroying the superposition and forcing the system into a definite state. The key point is that the universe behaves differently depending on whether information about the system is accessible or not. Observation, in this sense, is not passive. It participates in shaping reality. The idea that observation influences outcomes also appears in other quantum phenomena. Consider Schrödinger's famous thought experiment with the cat. A cat is placed in a box with a mechanism triggered by a radioactive atom. Until someone opens the box to check, the cat exists in a superposition of alive and dead states because the atom itself is in superposition. Opening the box, observing the system collapses the superposition into one definite outcome. The cat is either alive or dead. Schrödinger used this example not to suggest that cats literally exist in two states, but to illustrate how quantum superposition and observation conflict with our classical understanding of reality. Heisenberg's uncertainty principle is another manifestation of this concept. The principle states that certain pairs of properties, such as position and momentum, cannot be simultaneously measured with arbitrary precision. The more accurately we measure one property, the less accurately we can know the other. This is not a limitation of our instruments. It is a fundamental feature of the quantum world. The act of measuring one property disturbs the system in such a way that the other property becomes inherently uncertain. Observation changes what can be known about the system, again emphasizing the participatory role of measurement. Quantum experiments have repeatedly confirmed that observation changes outcomes. One famous example is the quantum eraser experiment. In this setup, scientists measure which path a photon takes in a double-slit apparatus, but then erase the which path information before detection. When the which path information is erased, the interference pattern reappears. The experiment shows that the physical behavior of particles depends on whether information about the system exists in principle, not just whether it is actively observed by a human. This challenges classical notions of causality and reality, revealing that observation and knowledge are intertwined with the behavior of quantum systems. The consequences of observation, dependent outcomes are profound. They force scientists to rethink the meaning of reality itself. In the quantum world, properties do not exist in a definite state independently of measurement. Reality is not a fixed backdrop. It is partially shaped by the act of observing. This challenges centuries of classical thinking and suggests a universe far stranger than everyday experience implies. The observer and the observed are connected in ways that defy classical intuition, highlighting the participatory nature of quantum physics. The practical implications are significant as well. Quantum technologies rely on controlling and preserving superpositions until measurement. Quantum computing, for example, exploits particles in superposed states to perform multiple calculations simultaneously. The outcome of the computation emerges only when the qubits are measured, collapsing their superpositions into specific results. Quantum cryptography also leverages the principle that observation changes outcomes. If an eavesdropper attempts to measure a quantum key, their observation alters the system and reveals intrusion. These applications demonstrate that the seemingly philosophical principle of observation shaping reality has real-world consequences and technological potential. At its core, the fact that observation changes outcomes in quantum experiments teaches us that the universe is not entirely independent of the information it contains. Unlike classical objects that exist in definite states regardless of whether we know about them, quantum particles exist in a dynamic balance of possibilities until measurement forces a choice. The act of observation is not passive. It is an interaction that fundamentally influences the state of the system. This is one of the most profound departures from classical physics, and one of the reasons why quantum mechanics is both astonishing and revolutionary. In conclusion, the principle that observation changes the outcome in quantum experiments reveals a universe in which reality is fluid, probabilistic, and participatory. The behavior of particles depends on whether or not they are measured, and the act of obtaining information determines the final state of the system. Experiments like the double-slit quantum eraser and thought experiments like Schrödinger's cat illustrate that observation is not a neutral process, but a transformative one. Heisenberg's uncertainty principle further emphasizes that measurement imposes limits on what can be known, demonstrating that knowledge and reality are intertwined. Observation does not just reveal reality, it helps create it, making quantum physics a radical departure from classical intuition and reshaping our understanding of the very nature of existence. Quantum entanglement is one of the most fascinating and mysterious phenomena in physics. At its core, entanglement describes a situation in which two or more particles become linked, so that the state of one particle is directly connected to the state of another, no matter how far apart they are. This connection is instantaneous. Changing the state of one particle immediately affects the state of its entangled partner. Albert Einstein famously referred to this as spooky action at a distance, because it seemed to defy the classical idea that nothing can influence something else faster than the speed of light. Yet, repeated experiments over decades have confirmed that entanglement is real and fundamental to the behavior of the quantum world. To understand entanglement, we must first recognize how it differs from classical correlations. In everyday life, two objects can appear correlated because of shared history or cause and effect relationships. For example, if two identical coins are flipped separately, they may show opposite faces because someone arranged them that way beforehand. This is a classical correlation. It can be explained by information or deterministic causes. Quantum entanglement, in contrast, cannot be explained by hidden variables or predetermined properties. Even if the entangled particles are separated by vast distances, their correlated behavior persists in a way that classical physics cannot account for. When one particle is measured, the state of the other is determined instantaneously, regardless of distance. One of the simplest ways to visualize entanglement is through the concept of spin, an intrinsic property of particles. Imagine two electrons prepared in an entangled state such that their spins are opposite. If one is measured to be up, the other must be down. Before measurement, however, neither electron has a definite spin. Each exists in a superposition of both up and down states. Only when one particle's spin is measured does the superposition collapse, instantly determining the spin of the other particle, even if it is light years away. The astonishing part is that this outcome is not determined until measurement, meaning the particles are genuinely connected across space and cannot be described independently. The phenomenon of entanglement challenges our classical intuitions about locality and causality. Classical physics assumes that objects can only influence each other through direct interaction or signals traveling at finite speeds, bounded by the speed of light. Entangled particles appear to bypass this limit. A measurement on one particle instantly affects the state of the other, even if no signal can physically travel between them. This does not violate relativity, however, because entanglement cannot be used to transmit information faster than light. The correlation is real and instantaneous, but it cannot be controlled to send messages. Nevertheless, it fundamentally alters our understanding of how particles are connected in the universe. Experiments testing entanglement often use photons because they are easy to manipulate and measure. In a typical experiment, a pair of photons is created from a single source in such a way that their polarization states are entangled. The photons are then sent to distant detectors, often separated by kilometers. When researchers measure the polarization of one photon, they immediately know the polarization of the other, regardless of distance. Countless experiments, including those performed with increasingly stringent controls, have confirmed the predictions of quantum mechanics. Entangled particles are correlated in ways that cannot be explained by any local hidden variables. These results provide strong evidence that entanglement is a real and unavoidable feature of the quantum world. Entanglement also plays a critical role in understanding the non-classical structure of reality. It reveals that particles are not always independent entities. Instead, they can form a single quantum system, even when physically separated. In other words, the universe at the quantum level is interconnected in ways that defy our macroscopic experience. This non-locality is one of the reasons quantum physics is so counterintuitive. It implies that the properties of particles are not fully determined in isolation, but depend on the larger entangled system of which they are a part. Reality is fundamentally relational, not strictly individual. The practical applications of entanglement are both groundbreaking and rapidly expanding. One of the most promising areas is quantum computing. Quantum computers exploit entanglement to link qubits, creating correlations that allow simultaneous calculations across multiple states. Entangled qubits can perform complex operations exponentially faster than classical bits, enabling solutions to problems that would be impossible for conventional computers. Entanglement is also essential for quantum teleportation, a process in which the state of a particle is transferred instantaneously to another distant particle using entangled pairs. While no matter or energy travels faster than light, the information describing the quantum state effectively moves instantly, a feat that would be unimaginable without entanglement. Quantum cryptography is another transformative application. Entangled particles can create encryption schemes that are theoretically unbreakable. Any attempt to eavesdrop on the entangled particles disturbs their correlations, immediately revealing the intrusion. This ensures secure communication channels far beyond the capabilities of classical cryptography. The ability to use entanglement for real-world technologies demonstrates that what once seemed spooky is not just a curiosity. It is a resource that can be harnessed in powerful ways. Entanglement also deepens our philosophical understanding of reality. It suggests that separateness is an illusion at the quantum level. Particles can behave as though they are part of a unified system, regardless of distance. This challenges traditional ideas about space and independence. The universe may be more interconnected than our senses or classical physics indicate. Some interpretations of quantum mechanics even propose that entanglement is a fundamental feature underlying spacetime itself, hinting at deep links between quantum physics and the structure of cosmos. The counterintuitive nature of entanglement is highlighted by thought experiments like the Einstein, Podolsky, Rosen-Epper paradox. Einstein, Podolsky, and Rosen argued that if quantum mechanics were complete, entanglement would allow instantaneous influence across distance, which seemed impossible. They suggested that hidden variables must exist to preserve locality. However, later experiments, particularly those testing Bell's inequalities, showed that no hidden variables can explain the observed correlations. Quantum mechanics, with all its non-local strangeness, accurately predicts entangled behavior. The universe is not just probabilistic at the small scale. It is fundamentally interconnected in ways that defy classical separations. Even everyday objects may owe their stability to entanglement. Atoms and molecules form coherent structures because the quantum states of their components are interdependent. While we do not see the effects of entanglement directly in the macroscopic world, it underlies the behavior of matter at every level. The cohesion of materials, chemical bonding, and the structure of complex molecules all rely on quantum correlations, highlighting the hidden but vital role of entanglement in the physical world. In summary, entanglement links particles instantly across distance, creating correlations that defy classical intuition. The state of one particle is directly connected to the state of another, regardless of separation. This phenomenon challenges our understanding of space, independence, and causality, yet it has been repeatedly confirmed through experiments. Entanglement is not only a cornerstone of quantum theory, but also a practical resource for quantum computing, secure communication, and emerging technologies. Philosophically, it forces us to reconsider the nature of reality itself. The universe is interconnected, relational, and far stranger than the classical view suggests. Understanding entanglement gives us a glimpse into the deep, hidden structure of the quantum world, where connections transcend distance and reality is woven from the fabric of correlation itself. Quantum uncertainty is one of the central pillars of quantum physics, often misunderstood both by scientists and the public. Unlike classical uncertainty, which arises from incomplete knowledge or measurement limitations, quantum uncertainty is an intrinsic property of nature. It is not a flaw, nor a technical deficiency in our instruments, nor a gap in our understanding of the universe. It is a fundamental limit imposed by the very structure of reality at the microscopic scale. Accepting this idea requires a shift in thinking. Nature does not provide us with perfect precision at small scales, and that is not a weakness. It is a defining feature of the quantum world. At the heart of quantum uncertainty lies Heisenberg's uncertainty principle, formulated by Werner Heisenberg in 1927. The principle states that certain pairs of complementary properties, such as a particle's position and momentum, cannot both be known to arbitrary precision simultaneously. The more accurately you measure one property, the less accurately you can know the other. This is not because of the imperfections of measurement tools, but because particles do not possess precise, fixed values for these properties until they are measured. The uncertainty is baked into the very fabric of quantum reality. Nature sets a boundary, a limit to how much can be simultaneously known, and that limit is absolute. To understand this, consider the analogy of trying to determine the position and speed of a particle using light. Classical intuition might suggest that shining a light on the particle could pinpoint its location without disturbing it. But photons of light carry momentum, and when they interact with a particle, they impart some of that momentum. Using higher energy light to get better positional accuracy disturbs the particle's motion more significantly. This illustrates the trade off between precision in position and momentum, but in reality, the uncertainty principle is more fundamental than just a practical measurement disturbance. Even in a perfectly isolated system, the particle's position and momentum cannot both have precise values simultaneously. This intrinsic limitation reflects the probabilistic nature of quantum mechanics and the wave-like character of particles. The uncertainty principle has profound implications for how we understand matter and energy. In the classical world, one might imagine a particle tracing a definite path through space, with a well-defined speed at every instant. In the quantum world, the particle is described by a wave function, a mathematical object that encodes probabilities for its position, momentum, energy, and other properties. These probabilities are spread out, reflecting the uncertainty inherent in the system. The particle is not simply unknown. It is genuinely indeterminate in its unmeasured properties. The probabilistic nature of quantum mechanics ensures that reality itself is not deterministic at microscopic scales. This is a radical departure from classical intuition, which assumes that with enough information, the future can be perfectly predicted. Quantum uncertainty is not merely an abstract principle. It has tangible, observable consequences. For example, It prevents electrons in atoms from collapsing into the nucleus. If electrons were particles with perfectly defined positions and momenta, they would spiral into the nucleus under the force of attraction, causing atoms to collapse. However, the uncertainty principle ensures that electrons must occupy a range of positions and momenta. This natural fuzziness stabilizes matter, allowing atoms and molecules to exist, form bonds, and build the complex structures necessary for life. Without quantum uncertainty, the universe as we know it could not exist. The limit imposed by uncertainty is not a defect. It is the very mechanism that enables stability and diversity in the material world. Another consequence of quantum uncertainty is zero-point energy, the lowest possible energy that a quantum system can possess. Even at absolute zero, particles in quantum systems continue to exhibit motion because they cannot simultaneously have zero momentum and a precise position. This residual motion is a direct manifestation of uncertainty and has practical implications in phenomena such as superconductivity, superfluidity, and the behavior of semiconductors. It illustrates that uncertainty is not a theoretical inconvenience. It is an active, observable feature of physical systems. Quantum uncertainty also underpins many modern technologies. Semiconductors, lasers, and magnetic resonance imaging MRI all rely on the probabilistic behavior of particles. Quantum tunneling, which allows particles to pass through barriers they could not cross classically, is directly related to the uncertainty principle. Without uncertainty, electrons could not escape potential barriers in transistors, and devices like flash memory, LEDs, and even the nuclear reactions powering the sun would not function as they do. Quantum uncertainty is a built-in property of nature that enables both stability and functionality, providing the foundation for the technological revolution of the 20th and 21st centuries. Philosophically, accepting quantum uncertainty challenges the deterministic world, that dominated science since Newton. In classical mechanics, knowing the exact state of a system at one moment allows perfect prediction of its future. Quantum mechanics shows that such determinism fails at the fundamental level. Even with complete knowledge of a system's wave function, we can only predict probabilities of outcomes, not certainties. This does not signify ignorance or incomplete theory. It reflects the true nature of the universe. Nature is probabilistic, not deterministic, and quantum uncertainty defines the limits of knowledge and predictability. Importantly, uncertainty is also a tool, not a barrier. It allows physicists to explore phenomena that classical mechanics cannot explain. The statistical patterns emerging from uncertain systems give rise to interference effects, energy quantization, and the unique behavior of atoms and subatomic particles. By understanding and applying uncertainty, scientists have developed quantum mechanics as a predictive and experimentally verified framework. Far from being a flaw, uncertainty is an essential feature that guides the rules governing the microscopic world. Quantum uncertainty also provides insight into the connection between measurement and reality. When we measure a particle's property, we select one outcome from the range of probabilities described by its wave function. The act of measurement itself is inherently linked to uncertainty, because it collapses multiple potential states into a single observable outcome. The measurement does not reveal a pre-existing value. It shapes which outcome becomes manifest. This interplay between uncertainty and measurement is one of the key ways that quantum mechanics departs from classical physics, emphasizing the active role of interaction in defining reality. Finally, quantum uncertainty is a reminder of the richness and subtlety of nature. It teaches that limits are not weaknesses but essential characteristics of a functioning universe. Uncertainty enables diversity, stability, and innovation in the physical world. It allows particles to occupy different energy states, form bonds, and interact in ways that classical physics could never predict. Accepting quantum uncertainty is embracing a deeper understanding of how the universe operates at its most fundamental level. In conclusion, quantum uncertainty is not a flaw or imperfection. It is a natural limit imposed by the structure of reality. It emerges from the fundamental probabilistic nature of particles and the wave-like description of matter. It stabilizes atoms, enables the existence of complex matter, and powers essential technological applications. Heisenberg's uncertainty principle formalizes this natural limit, demonstrating that the universe has inherent boundaries on how much can be known simultaneously. Far from being a weakness, uncertainty is a source of structure, stability, and possibility. Understanding and accepting this principle is essential for grasping the quantum world and appreciating the subtle, probabilistic, and interconnected nature of reality itself. One of the most fundamental lessons of quantum physics is that reality at the microscopic level behaves in ways that are profoundly different from the classical world. While everyday objects appear solid, definite, and predictable, particles at small scales, electrons, photons, atoms, and subatomic particles do not follow deterministic paths. Instead, their behavior is fundamentally probabilistic. This means that even with perfect knowledge of a particle's initial state, we can only predict the likelihood of different outcomes, not guarantee a specific result. Reality at these scales is governed by probabilities, not fixed certainties, and this realization has revolutionized our understanding of the universe. At the heart of this probabilistic nature is the wave function, a mathematical construct introduced in quantum mechanics to describe the state of a particle. The wave function encodes all possible information about a system, including the probabilities of finding the particle in various positions, with certain energies, or possessing specific properties. Unlike a classical particle, which has a definite position and momentum at all times, a quantum particle exists in a superposition of possibilities. Its properties are not fixed until an interaction or measurement occurs. The wave function evolves deterministically according to the Schrödinger equation, but the outcomes of specific measurements remain inherently probabilistic. Consider, for example, an electron in an atom. Classical intuition might suggest that the electron moves along a fixed orbit, like a planet around the sun. However, quantum mechanics tells a different story. The electron's position is described by a probability cloud, indicating the likelihood of finding it in various locations around the nucleus. The electron does not trace a single, fixed path. It exists in a spread of potential positions simultaneously. Only when we attempt to measure the electron's position does it collapse into one definite location. Even then, the outcome is random, determined by the probabilities encoded in the wave function. The reality of the electron is probabilistic until measured, reflecting the fundamental indeterminacy of quantum systems. This probabilistic nature is not limited to position. Momentum, energy, spin, and polarization also exhibit inherent uncertainty and probabilistic behavior. Heisenberg's uncertainty principle formalizes this relationship, showing that certain pairs of properties cannot be simultaneously known with arbitrary precision. The more accurately we measure one property, the less precisely we can know the other. This is not a technical limitation. It is an intrinsic feature of the quantum world. At small scales, reality does not provide fixed values. It offers distributions of possibilities, governed by precise mathematical rules. The probabilistic nature of quantum reality is vividly demonstrated in experiments such as the double-slit experiment. When individual particles, such as electrons or photons, are fired at a barrier with two slits, each particle behaves unpredictably in terms of where it lands on a detection screen. However, over many trials, a clear interference pattern emerges, a pattern that reflects the probabilities dictated by the wave function. Each particle's behavior is individually unpredictable, but the statistical distribution follows strict quantum rules. This shows that while reality is probabilistic at the level of single events, it is remarkably consistent and law-like at the level of large numbers, bridging the quantum and classical worlds. Entanglement further illustrates the probabilistic nature of small-scale reality. When particles become entangled, the outcome of measurements on one particle is correlated with the outcome of measurements on the other, no matter the distance between them. Yet the results of individual measurements are inherently random. We can predict correlations between particles, but not the specific result of any single observation. This combination of randomness and structured correlation exemplifies how probability governs quantum reality. Individual outcomes are uncertain, but statistical patterns follow exact quantum rules. The probabilistic character of quantum reality has profound philosophical implications. Classical physics suggested a universe that is deterministic. Given complete knowledge of the present, the future can, in principle, be predicted exactly. Quantum mechanics shatters this notion. Even with perfect information about a system's wave function, we cannot predict individual events with certainty. The universe at its core is probabilistic, not deterministic. This realization forces us to rethink fundamental concepts of causality, prediction, and the nature of physical laws. Rather than a fixed script unfolding in time, reality at small scales is a web of potentialities, with probabilities guiding how events manifest. Despite the randomness at the microscopic level, probabilistic quantum behavior produces remarkably stable and predictable macroscopic phenomena. The probabilistic positions of electrons in atoms create the structure of chemical elements, determining the properties of matter. Probabilistic energy levels govern chemical reactions, molecular bonding, and the behavior of materials. The stable macroscopic world emerges from the underlying probabilistic behavior of countless particles. What appears fixed and deterministic at large scales is built upon a foundation of small-scale uncertainty and probability. Quantum probabilistic reality also enables remarkable technological innovations. Semiconductors, lasers, and superconductors all rely on the probabilistic behavior of electrons and photons. Quantum tunneling, which allows particles to cross energy barriers they could not overcome classically, is a direct consequence of probabilistic wave functions. Quantum computing harnesses the superposition and probabilistic outcomes of qubits to perform calculations beyond the reach of classical machines. Without accepting the fundamental probabilistic nature of particles, these technologies would be impossible. Moreover, probabilistic reality challenges our understanding of observation and measurement. In classical physics, observing a system does not fundamentally alter its state. In quantum physics, measurement interacts with a probabilistic system, collapsing multiple possibilities into a single outcome. Yet which outcome occurs cannot be predicted with certainty, only the likelihood of each possible result. This intertwining of measurement, probability, and physical reality shows that the act of observation is inseparable from the probabilistic character of small-scale phenomena. In summary, reality at small scales is fundamentally probabilistic, not fixed. Quantum particles do not have definite properties until they are measured. They exist as superpositions of possibilities described by a wave function. Heisenberg's uncertainty principle formalizes the intrinsic limits of knowledge, while experiments like the double, slit, and entanglement studies confirm that randomness governs individual outcomes. Despite this inherent unpredictability, stable patterns emerge at larger scales, giving rise to the macroscopic world we experience. Probabilistic quantum behavior underpins both the structure of matter and modern technology, revealing a universe far stranger and more fascinating than classical intuition suggests. Accepting this principle allows us to understand the quantum world not as chaotic or flawed, but as a finely tuned system governed by probabilities, where uncertainty is a natural and essential feature of reality itself. Quantum physics may seem like an abstract, almost philosophical field, exploring the bizarre behaviors of tiny particles at the subatomic level. Yet, the principles of quantum mechanics are not confined to theoretical musings. They have direct, transformative effects on the technologies that define the modern world. From lasers to computers, from medical imaging to secure communication, quantum phenomena underpin some of the most revolutionary tools of the 20th and 21st centuries. Understanding these technologies requires understanding the quantum principles that make them possible. One of the most well-known applications of quantum mechanics is the laser, which stands for light amplification by stimulated emission of radiation. The laser is not just a source of coherent light. It is a practical manifestation of quantum principles at work. The key quantum concept behind lasers is energy quantization. Electrons in atoms can only occupy discrete energy levels, and transitions between these levels release or absorb photons with specific energies. In a laser, electrons are excited to higher energy levels, and when they return to lower levels, they emit photons. Crucially, quantum mechanics allows these photons to stimulate the emission of additional identical photons, a process called stimulated emission. The result is a coherent, focused beam of light with highly predictable properties. Without the quantum understanding of energy levels and photon interactions, lasers would not exist. Today, lasers are essential in countless technologies, including optical communications, barcode scanners, surgical equipment, and high-precision manufacturing. Quantum mechanics also forms the foundation of modern electronics, including semiconductors and transistors. Classical physics cannot fully explain the behavior of electrons in materials like silicon, but quantum mechanics provides the necessary framework. Electrons occupy quantized energy bands, with a band gap separating the conduction and valence bands. The movement of electrons across these bands, governed by quantum tunneling and probabilistic occupancy, allows semiconductors to switch and amplify electrical signals. Transistors, which rely on the controlled flow of electrons through these quantum energy bands, are the building blocks of modern computers. The ability to manipulate electron behavior at the quantum level enables processors to perform billions of calculations per second, powering everything from smartphones to supercomputers. Quantum principles also enable quantum tunneling, a phenomenon where particles can pass through energy barriers that would be insurmountable in classical physics. This effect is not just a theoretical curiosity. it has practical applications in modern electronics. Flash memory, for example, relies on tunneling to store and erase data. In these devices, electrons tunnel through insulating barriers to change the charge state of memory cells. Without tunneling, non-volatile memory, which retains information even when power is off, would be impossible. Similarly, scanning tunneling microscopes, which allow scientists to image surfaces at the atomic level, rely on tunneling to detect electrons and map atomic positions with incredible precision. Quantum tunneling transforms abstract quantum behaviors into tangible tools for technology and research. Quantum superposition and entanglement, once considered purely theoretical, are now at the heart of emerging quantum computing technologies. Classical computers process information in bits, which exist as either 0 or 1. Quantum computers, however, use qubits, which can exist in superpositions of both 0 and 1 simultaneously. This property allows quantum computers to perform many calculations at once, drastically increasing computational power for certain tasks. Entanglement links qubits in a way that creates correlations impossible in classical systems, enabling complex computations and error correction. Companies and research institutions worldwide are actively developing quantum computers that can solve problems beyond the reach of classical machines, such as simulating molecular interactions, drug discovery, optimizing logistics networks, and tackling cryptography challenges. These technologies demonstrate that quantum principles directly drive the next generation of computational tools. Quantum mechanics also underpins medical imaging technologies like magnetic resonance imaging (MRI). In MRI, atomic nuclei, primarily hydrogen protons in the body, are exposed to strong magnetic fields. The nuclei align with the field, and when a radio frequency pulse is applied, they transition between quantum spin states. The nuclei then emit signals as they relax back to their original states, and these signals are detected and transformed into detailed images of internal tissues. Understanding and manipulating the quantum spin of nuclei is essential to this imaging technique, which has revolutionized medical diagnostics by providing non-invasive, high-resolution views of organs, tissues, and even the brain's functional activity. Quantum cryptography is another area where quantum principles directly impact modern technology. Quantum key distribution, QKD, leverages the fact that observation affects quantum systems. By encoding information in entangled particles or individual photons, quantum cryptography ensures that any attempt to eavesdrop will disturb the system, immediately revealing the intrusion. This creates communication channels that are theoretically unbreakable, far surpassing the security capabilities of classical cryptography. Financial institutions, government communications, and secure data networks increasingly explore quantum cryptography as a safeguard against future threats, including those posed by quantum computers capable of breaking traditional encryption. Photovoltaic cells, which convert sunlight into electricity, also rely on quantum principles. When photons strike a solar cell, they excite electrons from the valence band to the conduction band, creating electron-hole pairs. The quantized energy levels of electrons and the probabilistic absorption of photons are quantum effects that allow solar cells to convert light energy into electrical energy efficiently. Understanding the quantum interactions between light and matter has led to the design of more efficient photovoltaic materials and is central to developing next-generation solar technology. Even everyday technologies such as LED light-emitting diodes depend on quantum mechanics. Electrons recombine with holes in semiconductors, releasing energy in the form of photons. The color and efficiency of LED are determined by the energy difference between electron states, an inherently quantum property. Without the principles of quantum mechanics, we would not have efficient, durable lighting or display technologies that power billions of devices worldwide. In summary, quantum phenomena are not abstract curiosities confined to laboratories. They are the engines powering modern technologies. Lasers, semiconductors, transistors, quantum computers, MRI machines, quantum cryptography, photovoltaic cells, LEDs, and countless other technologies all rely on the peculiar yet predictable behavior of particles governed by quantum mechanics. Quantum principles such as superposition, entanglement, energy quantization, tunneling, and probabilistic states transform the behavior of matter and light, enabling tools that shape our everyday lives. These technologies reveal that the strange and counterintuitive rules of the quantum world are not just theoretical. They are the foundations of the practical, technological universe we inhabit. Understanding these applications demonstrates the tangible power of quantum physics. It shows that the weirdness of the subatomic world is not irrelevant. It is essential. From the devices in our pockets to the cutting-edge instruments exploring the universe, quantum mechanics drives progress and innovation. The very future of computing, communication, medicine, and energy technology depends on harnessing the principles of a world where particles behave in ways that challenge our classical intuition but open doors to possibilities beyond imagination.